We continue our discussions of the application of mean value theorem. We will see how powerful that idea is. We had made the statement yesterday that mean value theorem is powerful, blah blah blah. We can give physical explanations, everything, but even in calculus, lot of good ideas come out because you keep on applying the mean value theorem. One such idea I will now speak on is this idea of monotone functions or monotonic functions. So, we will talk about two classes of functions, increasing and decreasing. Increasing, decreasing. So, take any function f, say from R to R, and an interval I in R. If that for any x y in I with x greater than y, if it implies that fy is strictly bigger than fx, then the function is called increasing. And the decreasing thing is the same, where whenever x is strictly bigger than y, the function value should decrease. So when x is strictly bigger than y, fx should be strictly bigger than fy. This is increasing. Sorry, I made a mistake. I just wrote the decreasing definition. So increasing means when x is bigger than y, f of x should also be strictly bigger than y. If x is bigger than y, it should imply that f of x should be strictly lesser than fy. So that is the meaning of decreasing. So there are certain other definitions which we have, like non-increasing, non-decreasing. Non-increasing means, and non-decreasing. So non-increasing means it doesn't increase. If it at all anything happens, it either remains same or it decreases. So if x is strictly bigger than y, then it should imply that f of x is less than or equal to fy. So it is not increasing. It could remain equal, but it won't be increase. And here, if x is strictly bigger than y, then fx is greater than or equal to fy. Fx need not be always strictly greater, even if I have these to be strictly greater. So one of the most simple and elegant applications of the mean value theorem is the following, is that if f is differentiable and f dash x is strictly greater than 0 for all x, say in an interval a b, then f is increasing. So this term, after these terms have been coined in the literature, some people started calling this strictly increasing and strictly decreasing, but we will keep on calling them increasing and decreasing. Increasing in AB. So example, if you draw the graph of an increasing function, y equal to x cube. So you take any x and any y, doesn't matter, the function value is increasing, the function value is increasing. So whenever you have x and you have y, whenever x is bigger than y, fx is bigger than fy. So how do I prove this fact? The fact is the following. So take any y and z, arbitrary y and z in AB, then by the mean value theorem you have that Fy minus Fz. So, take y and z in AB. So, among them either y is bigger than z or y equal to z or y is less than z. So, we will choose, obviously we can't choose y equal to z, then we are then the function value remains same. So, choose it in such a way that y is strictly bigger than z. So, now then by definition Fy minus Fz by y minus z, okay, this must be equal to f dash w for some w in the open interval yz, that is a MVT. But then this open interval yz is a subset of the open interval AB, as a result of which f dash w is strictly bigger than 0. So, since f dash w is strictly bigger than 0, it simply implies that Fy minus Fz by y minus z is strictly bigger than 0. Now, y, so you multiply both sides by y minus z is strictly bigger than 0. So, this inequality does not change. So, it simply means that Fy is strictly bigger than Fz, and which shows that it is increasing. I would leave it to you to write down a similar result for the decreasing case when you have Fx is strictly less than 0. So, if f is differentiable and f dash x is strictly less than 0 in an interval AB, then f is decreasing. Now, what I want to say is that this is a sufficient condition. It tells me that if I know this nature of the derivative, I can tell the nature of the function. As I told you, whenever you have some information of the about the derivative and you need an information of the function, just go apply this beautiful Lagrange mean value theorem, and that would lead to the answer. See how beautiful and simple things are. And now you might ask the reverse question, is this condition necessary? Whenever I have a strictly increasing function, is f dash x strictly bigger than 0? The answer is of course no. Converse is not true. Example is right there on the board, the x cube function. So, f x equal to x cube, this is strictly increasing. But f dash 0 is 0. It is a very prototype and standard example in calculus that this is. So, the reverse is not true. But, so you cannot have any necessary condition here, but you have a sufficient condition. But you will take, for example, this kind of stuff. Suppose you have a differential function which is non-increasing or say non-decreasing, then you can have necessary conditions. For example, if you take 2 points x and x plus h where h is positive. So, f of x plus h minus f x is greater than or equal to 0. If it is say non-decreasing, because h is greater than 0. So, x plus h is strictly bigger than h, x plus h is strictly bigger than x. So, which means f of x plus h is either equal or strictly greater than f x, that is greater than or equal to f x. Then because h is positive, you simply divide by h. Then you take the limit as h tends to 0, that will simply tell you that f dash x is greater than or equal to 0. So, for this case the necessary condition can be implied, but this does not at all mean f dash x greater than or equal to 0. Okay. So, we might now get the idea that okay, f dash greater than equal to 0 might not always imply this condition, means this one. See, we know that in that case it is not sufficient, but in in the strict case it is sufficient but not necessary. But here is it both necessary and sufficient, that is what we want to check. It is necessary is obvious because here I have taken the limit h going to 0 plus, but because the derivative exists, that is the derivative, and hence we get it. But what about the reverse in this case? That is the question that I want to ask. Again the mean value theorem would be helping. Suppose on an interval I know that f dash x is greater than equal to 0, say on interval a b. Now you take any point again y and z, such that y is strictly bigger than z. Then again apply the mean value theorem. F dash w for some w So, here you see f double dash w, so for some w in y z, for some w in say z y. Here it should be also z y because z is lesser than y. So, z should be on the left and y should be on the right. Sorry, I am writing fast, so when I write fast I sometimes slip. So, that is human. Mathematics, by the way, is human endeavor, something that we need to remember. So, now what would happen, that this is greater than equal to 0. So, this is true for any w in z y, and this z y is inside this interval, z y is inside the interval say a b. So, then f y minus f z is greater than equal to 0, which proves that it is non-decreasing. So, this condition is both necessary and sufficient, and that is the reason this non-decreasing and these sort of functions have been defined, that you can now pose through the derivative both a necessary and sufficient condition, both a backward and forward condition. Now, we had mentioned about this issue of the second derivative. When we do optimization, we do second derivative, use the second derivative if the function is twice differentiable to determine whether your given point, critical point f dash a equal to 0, that a is either a maxima or minima or whatever, nothing. So, that has to be determined by the sign of the second derivative. That information we have written, and many of you who are already done calculus in high school would definitely know that fact. But we are now going to use again what we have just learned to prove this simple fact, and let us now try to prove that whatever we have learned about increasing and decreasing functions, let us now try to prove that the sign of the second derivative is crucial in determining the actual nature of a critical point. If you remember, critical point is a point at where the derivative vanishes, but a critical point need not be a point of maxima or minima. For example, the point x equal to 0 in function f x equal to x cube, which you already know that that is not a point of maxima and minima, but is, again I remind you, but is a point where the derivative vanishes. So, my result, which I now really write down as a theorem, that this is important. Assume f is from R to R, do not bother about this interval and all this stuff. And because we had been really bothered much about unconstant optimization in the sense that we are minimizing over the whole of R. So, the function naturally needs to be defined on the whole of R. So, function is from R to R and differentiable. Let f dash x star is equal to 0. So, x star is a critical point. then if f is, maybe I should write f is more 2 and twice continuously differentiable. The second derivative exists and is continuous. The second derivative is also a function of x. Then if f double dash x star is strictly greater than 0, then x star is a strict local minimum. X star is a strict local minimum point. Now, how do I prove it? F double dash A, how do I define this? Maybe twice continuously differentiable might not be required, just twice differentiable is required, but in standard problems, either use of this word twice continuously differentiable would be helpful when it will talk about Taylor's theorem and use Taylor's theorem to actually prove this result. We will prove this result again, but still we would we will prove this result again in a more different way, but still does not matter if you keep this. If we just keep it continuous, when it is second differentiable, we do not want to take it continuously second differentiable, that would do. Second derivative exists at x star, sorry, is enough. So, that is limit of h tends to 0, f of x star plus h minus f of x star by h. Now, f of x star is equal to 0. So, and f double dash x star is greater than 0. So, this is nothing but lim of h tends to 0 f of x star plus h by h. Now, because this is because f double dash x star is strictly bigger than 0, so I am writing since, it would imply that limit h tends to 0 f of x star plus h by h is strictly bigger than 0. So, now here is some reasoning that we will make that you be very careful about. Now what is that limit? That limit is f double dash x, limit of this is f double dash x, f double dash x is positive. So, what does it mean? Given choose an epsilon, choose epsilon greater than 0 such that f double dash x star minus epsilon is strictly greater than 0. This is possible because f double dash x is not equal to 0, f double dash x star is strictly bigger than 0. So, if I take away very small quantity, it will still remain positive. That is so between 0 and any positive number there is infinite amount of positive, there are countably infinite positive numbers, and that is the key of making this statement. So, I can choose this. So, now for such epsilon there exists delta greater than 0 such that So, here there was a minus f x star. So, x star plus h minus f x star. So, such that whenever mod h, this one is within this domain, then what we have? We have f of x star plus h is strictly less than f of x star plus epsilon, sorry, f of x star plus epsilon, and also strictly greater than f of x star minus epsilon. But f of x star minus epsilon, if you look at, I have already chosen the epsilon such that this is strictly bigger than 0. So, for such an epsilon I can get a delta for which this is true. So, there is a delta such that whenever mod h is strictly less than delta, and obviously h is not 0, you will have, so for all h with this, it implies that f of x star plus h is strictly bigger than 0. So, it says for h sufficiently small, h whose the real number h whose absolute value is sufficiently small for which this is true. So, what does it say? Sorry, I have made a big mistake, big mistake. Here it should be f dash because we are taking the second derivative. So, it is f dash. So, it is f dash. So, here it is f dash, here it is f double dash. Right. So, please understand. So, I am taking the second derivative. So, it is the derivative of the derivative. So, I made a rather I would, if I type it out, we would call nowadays a typographical error. So, it is a chalk error rather that I have forgotten this sign. So, what does it show? That in this small interval, f dash plus x star h is strictly bigger than 0. So, basically if so, f dash plus x plus h by h, sorry, I made a mistake. So, by h this is strictly bigger than 0. So, if h is now positive, if h is positive, what I have? So, if h is positive, I will have f of x star plus h to be strictly greater than 0 whenever h is less than delta. But if h is negative, I will multiply both sides by h because I want to cancel this h. I just want information about f dash x star plus h. So, from x star to x star plus h means up to x star plus delta, f dash of x star plus h is strictly bigger than 0. But if h is negative, that is you are moving towards the left of x star plus h, when h is positive, x star plus h dash, say when h dash is a negative number. So, if h is negative, which is this case, then f dash, because I will multiply by negative number, this sign will change. So, f dash x star plus h is negative. So, again I will apply the theorem that we have already learnt here. So, because whenever h is positive and h is less than delta, and whenever h is negative and greater than minus delta, you have this whenever h is positive and less than delta, this happens whenever h is, obviously here I should have h less than delta, here I should have or rather when I can just write mod h less than delta, mod h less than delta, and h not equal to 0. Obviously I am not writing repeatedly because h is obviously assumed to be not equal to 0. So, when h is positive I have this. So, between x star and x star plus h the function is increasing, and between x star and x star minus h the function is strictly decreasing, strictly, please understand the term. So, from between x star in this interval, f is strictly increasing, and so for any z in x star plus x, x star plus h, what would happen? Any z, any x star plus h, I will have f of x star strictly less than f of x star 2 is strictly less than f of z. Similarly, when I take x star plus h dash to x star, then for any z dash element of x star plus h dash to x star, what will I have? I will have f of z dash, because this is strictly increasing, here it is strictly decreasing. So, the value of f would decrease, the function value decreases, f of z dash is bigger than f of x star. So, what is f of x star? F of x star, because z, obviously I am taking a z dash which is not equal to x star, because I have taken it in the open interval. So, for any z dash or z or any in the interval, say x plus h and x minus h, in this interval x star plus h and x star minus h, whatever z I take, it does not matter. If it is not equal to x star, the functional value is strictly bigger, and hence it is a strict local minimizer. So, this is a very important result, and lot of things you see we are continuously using this epsilon delta argument. Sorry for some typos rather, but please follow the argument once again. Here you are taking the second derivative of the derivative and arguing in this fashion, in the using the epsilon delta fashion, and that is exactly where we land up. There are several things which cannot be told in this class, but will appear in the notes, but I would just like to tell you that notes will not appear immediately. It will take time to correct the notes and put things. Many things cannot be told in the class, there are time restriction, but hence we will do something, we will write something in the notes which are not in the class and which will not be told in the class. So, we will end this discussion, we will take 5 or 6 minutes more to talk about what is called inverse functions. When does a function have an inverse and what is the meaning of inverse? This is something very important. So, we will just work it out. So, giving a very brief idea of what inverse function possibly is. So, basically you know what inverse function is. For example, if I have y is equal to x plus 5, then inverse function is now to write here y is a function of x, and inverse function means I write x as a function of y. So, here see, if somebody asks me, it is traditional in mathematics to tell me what is the inverse function corresponding to this function, I will say f inverse of x is x minus 5. Actually this is y, but this is because these are dummy variables, you can just, this is a traditional way of writing it. So, here is your domain and here is your range. So, this is a very important concept. So, you see there can be 2 points which are going to the same 2 x's in A, x1, x2, which can go to the same y. So, what is f inverse y? F inverse y actually means the inverse image of y. So, it means the collection of all x in say A such that f of x is equal to y. That is the meaning of the inverse function. So, in this particular case, for example, here f inverse y is equal to x1, x2. So, corresponding to this y, I have 2 elements which are corresponding. So, which means here the inverse function really does not satisfy the definition of a function. For a definition of a function, every y should be mapped to only 1x, exactly 1x. 2 different y's can be mapped to, if you think that if the function has to have an inverse, you can say okay, then can 2 different x's be mapped to, can a single x be, 2 different y's be mapped to a single x? No, it cannot be, but then it will break that this is a function from this side. to maintain that it is a function from both sides, that is, I can write y as a function of x and x also as a function of y. If both things can be done, then 1x should correspond to 1y only. So, that is called a 1-to-1 correspondence or a bijective mapping, about which you have some idea in high school. So, this is so this is the very basic idea of an inverse mapping. You have to very clearly understand. For example, I take two simple functions f(x) equal to x square and f(x) is equal to x cube. Look at f(x) equal to x square. Does it so if the inverse image has more than, for a given y, if it has more than one element, then this inverse is not a function, it is called a set valued map. But for every y in B, if the inverse image has only one element corresponding to it, x, then we said that the function has an inverse. For example, here take the number 4, y equal to 4. Y equal to 4 is achieved by two numbers, 2 and minus 2. The square of minus 2 is 4, square of 2 is 4. So, in this case, f inverse of 4 is a set 2 minus 2. So, this function x square does not have an inverse, but f(x) equal to x cube does have an inverse. So, how do I look at it? Here x and here y. So, x is viewed as a function of y. I can just look at like this and think of x now viewed as a function of y. Here y is first viewed as a function of x, and then if I look at it, x is viewed as a function of y. And if you observe, take any y, there is only one x corresponding to y. Take any y, there is only one x corresponding to y. So, there is a bijection between the x's and y's. So, which means this function has an inverse, and f inverse x as you y equal to x cube, so x cube is x is cube root of y, but usually this is the standard way of writing. Obviously, you can write f inverse y is cube root of y, that is also acceptable. So, this is inverse, this is the, but from this function you might have some doubt in this sense that there must be some relation between a continuous function and increasing function. So, here we state this result and we end our talk today. You will find more information in the notes, is that if a continuous function is 1-to-1, that there is a 1-to-1 correspondence between the x's and y's, then it is either a decreasing function or an increasing function. If f is continuous and 1-to-1, so it means it has an inverse, then f is either decreasing or increasing. So, this is something very important, and with this we end our, maybe I should write it more near C. With this we end today's lecture, and in the next class we are going to talk about a very fascinating way of using the derivative to actually solve equations of the form f(x) equal to 0. Because this solution of equations of the form f(x) equal to 0 is required in many places. For example, if you want to solve f dash x equal to 0, it might not always be easy to solve f dash x equal to 0. So, you have to adopt some other techniques which are called numerical techniques, and in that the derivative plays clearly a major role, and that was first espoused by none other than the great Isaac Newton, possibly the greatest scientist of all times. So, we will talk about Newton method, or sometimes called the Newton-Raphson method, for solving fx equal to 0 using the notion of a derivative. Obviously, we are assuming that the derivative exists. Thank you very much.